Okay, so in this question, in order for you to draw the velocity time graph, you need to understand that there are actually three parts to this. So the first part of this is, of course, the acceleration from rest to 50 meters per second. So when we draw the graph, we understand that this is actually a velocity time graph. So the y-axis is velocity, the x-axis is time per second. Alright, so from rest to 50 meters per second within 4 seconds. So we understand that it's actually a constant acceleration. So 4 seconds, 50 meters per second. So you will have this portion. So this is the first one. For the next part, I will draw in red. You realize that you are asked to actually draw the cyclist traveling at a constant speed for next 200 meters. So in this case, we know the distance traveled. We do not know how much time it takes, but we know that he's traveling at a constant speed of 50 meters per second. So 50 meters per second, for it to travel 200 meters, it will actually be another 4 seconds. So over here, we draw another 4 seconds. This is what you will have. So 4 seconds, inclusive of the previous 4 seconds, we will actually have 8 seconds. So this is time t equals to 8. And for the next part, I'm going to draw in blue. It has a constant deceleration in the next 5 seconds, so a straight line down all the way to 0. So 8 plus 5, in the next 5 seconds, we know that t equals to 13. And so this is actually the velocity time graph shown. Of course, what happens is that this is not drawn to scale. The gradient is also slightly off. Hence, but the overall shape is as such. Right, now for part B, we are supposed to find the total time taken. So by drawing the velocity time graph, we actually found out that the total time taken is actually 13 seconds. Now for part C, we would like to find the distance traveled in total. So distance traveled in total is actually the total area under the graph. So the area under a VT graph, where VT stands for velocity time, okay, is actually equals to distance traveled. So we understand that this is actually a trapezium, so you can actually use the trapezium formula, half a plus b times height. Now, so where is the a and where is the b? So I will highlight in yellow where is a, and highlight in green where is b. As for the height, I will highlight it in light blue. Okay, so this is where we have the height. Okay, so you can see that we are actually trying to make use of the different dimensions of a trapezium to find what's the area. So over here, the value of a is actually 4, the value of b will be 8, and the height itself is actually 50. So we will have half times 12 times 50, that's equivalent to 6 times 50, and so we will have 300 meters. So in total, the distance traveled is actually 300 meters. Okay, next we talk about the acceleration. So acceleration at time equals to time equals to 2 seconds. Okay, we recall that in order to find the acceleration, you need to find what's the gradient at that point. And you notice that the gradient at that point is actually the same as the gradient of the whole section. So instead of finding the gradient of that point, we can actually find the gradient of the whole section, which means that the acceleration at t equals to 2 is actually equals to the gradient of the line, okay, where we use the formula y2 minus y1 over x2 minus x1, or we can call it the rise over the run. So we will actually have 50 minus 0 divided by 4 minus 0. So that's actually 50 divided by 4. So we should have 12 0.5 meter per second square. Okay, so the last part, we're supposed to find what is the deceleration. So the deceleration in the last 5 seconds is actually very similar. So we just have to find the gradient at the last portion. Right, so for part E, to find the deceleration, okay, we need to use the acceleration formula. So acceleration is equals to 0 minus 50 divided by time taken of 5 seconds. So we have minus 10 meter per second square. And with that, therefore, the acceleration must be equals to just 10 meter per second square.